All right, let's dive right into this explainer. It's funny how math algorithms look beautifully perfect in a textbook, right? But the second you unleash them on the messy real world, everything gets incredibly complicated. Today, we are peeling back the mathematical layers to see how AI algorithms actually evolve to solve those increasingly complex, highly unpredictable real-world problems. We're not just looking at basic, perfectly straight lines here. We're going to see exactly how machine learning models adapt and survive when the real world throws them curves, absolute random noise, and rigid, strict categories.
We've got a brilliantly structured roadmap today to track this evolution. We'll be looking at 5 key stops: beyond the straight line, the probability of prices, the problem with categories, enter logistic regression, and finally the need for speed. Let's get right to it.
All right, Section 1, Beyond the Straight Line, looking at locally weighted regression.
So here's our first real roadblock. What happens when your data, like, say, housing prices over time, just curves and absolutely refuses to fit a perfectly straight line? Usually you'd reach for a parametric algorithm. You can think of this kind of like memorizing a single, compact mathematical formula for a test. Once you've got that formula down, you essentially just toss all the training data right out of your computer's memory. You simply don't need it anymore. But when data curves unpredictably, guessing the exact math feature to add, like, I don't know, a square root or a logarithm, is incredibly tough. To fix this, we pivot from parametric to non-parametric algorithms. If parametric is memorizing a simple formula, non-parametric is literally an open book test where you have to lug the entire massive textbook, meaning your whole data set, around with you everywhere. The parameters physically grow with your data because you're actively keeping all that training data in memory.
And honestly, this beautifully solves our curving problem. Think about it for a second. If you want to predict the price of a specific house, you wouldn't bother looking at home sales on the complete opposite side of town, right? No, you'd only look at the houses on that exact street or in that specific neighborhood. Well, locally weighted regression does exactly this. Instead of stubbornly fitting one rigid, unbending line to everything everywhere, it zooms in on the specific point you want to predict, it focuses its attention exclusively on the data points immediately surrounding it, and fits a custom line just for that local neighborhood. It gives those nearby points the most mathematical weight, using this bell curve shape to smoothly drop the weight of the further points down to absolute zero.
Now, the million-dollar question is, how do we actually define and control that local neighborhood? Well, we use a dial called the bandwidth parameter, or the Greek letter tau. I like to think of tau as a kind of Goldilocks dial. It determines exactly how fat or thin our weighting curves should be. Turn the dial way too high, make tau too broad, and you end up over-smoothing the data. You literally wash out all those subtle, important local nuances. But on the flip side, if you make it too thin, you get this incredibly jagged, erratic fit that basically neurotically overreacts to every single data point. So it's all about dialing in that perfect mathematical balance so it's, well, just right.
Moving on to Section 2, the probability of prices, and asking, why least squares?
This brings us to a really foundational question. Why do we universally default to minimizing least squares when we're fitting these lines in the first place? I mean, why not use absolute value or, I don't know, raise it to the power of 4? To understand this, we actually have to look at how real-world prices are determined. It's never just a perfect formula. There are always unmodeled effects. As the source material wonderfully points out, a house price might fluctuate simply because, well, maybe one day that seller is just in an unusually good mood. That random, unpredictable nature of real-world data, that human unpredictability, is mathematically captured as what we call Gaussian noise.
But here's the catch. To make the math actually work out, we have to make a pretty massive assumption about that noise. We have to assume these random errors are IID, independently and identically distributed. So what does that actually mean in plain English? It means the random error or noise affecting one house, say a seller suddenly discovering a massive termite problem, is completely independent of the error affecting another house 3 blocks away. One doesn't magically cause the other. Now, is this always perfectly true in the messy real world? Honestly, no, since neighborhoods can collectively trend up or down together. But making this assumption is mathematically necessary, and trust me, it gets us to an incredibly powerful model.
So that leaves us with a huge question. If our data is fundamentally full of this random, unpredictable Gaussian noise, what mathematical tool can we possibly use to confidently find the best fitting line? Like, how do we find optimal parameters when absolutely everything is being bumped around by random chance?
Enter maximum likelihood estimation, or MLE for short. This is this beautifully elegant statistical method where we choose the parameters that maximize the absolute probability of actually observing the data we literally have sitting right in front of us. And here is the amazing mathematical punchline. When you sit down, grab a pencil, and work out the calculus for maximizing the probability of data under Gaussian noise, it algebraically simplifies to the exact same formula as minimizing the squared errors. It's a total aha moment. That right there is exactly why we use least squares. It mathematically proves that minimizing our squared errors is the literal exact same thing as maximizing the probability of our data. It's not just some convenient tool we picked out of a hat. It is mathematically the absolute best possible approach.
All right, let's jump straight into Section 3, the problem with categories, specifically binary classification. So our model hits a massive brick wall when we stop predicting continuous numbers like housing prices and we start trying to predict strict categories. Think about high-stakes medical diagnoses, like predicting whether a tumor is benign or malignant. In binary classification, our answers are absolutely 100% constrained to just two possible outcomes, exactly 0 or exactly 1. There is 0 in between.
Because of that, drawing a traditional straight line for this is honestly a terrible idea. A straight line can output negative numbers, or numbers way larger than 1, which makes absolutely no sense when you're talking about strict probabilities. But it gets worse. Imagine a single massive outlier, say an exceptionally large tumor that's very clearly malignant. That one single outlier will wildly drag your entire mathematical boundary totally out of whack toward it. When you try to threshold that altered straight line at 50% to make a decision, that single extreme outlier has literally ruined your predictions for all the more ambiguous borderline cases. It forces your algorithm to misdiagnose patients. We absolutely, desperately need a better way.
Which brings us right to Section 4, Enter Logistic Regression and the Sigmoid Function. To fix this rigid boundary problem, we're bringing in the absolute workhorse of classification algorithms.
The secret sauce here is the sigmoid function, which is also known as the logistic function. You know, mathematicians love naming things after shapes, and the sigmoid is exactly that, an elegant S-shaped mathematical curve. What is so incredible about this specific curve is that it magically squashes any wild mathematical output, so it sits neatly between exactly 0 and exactly 1. So no matter how massively large or incredibly small your input is, the sigmoid function comfortably maps it into a perfectly valid, understandable probability.
You can really think of this as a three-step assembly line for our machine's thought process. First up, we input our raw features, like say the tumor size. Second, we calculate our standard linear function, just exactly like we used to. But then, step 3, we don't just stop there. We take that raw linear result and pass it straight through our S-shaped sigmoid function. This brilliant little assembly line takes raw data and transforms it into a highly accurate probability score, neatly and safely boxed in between 0 and 1.
Now, how do we actually train this thing? Well, because our core equation changed, our cost function has to change right along with it. We use a concept called log likelihood. And instead of descending down into a valley to minimize errors, like we did with least squares, we are now basically climbing a mountain of probability. We use an algorithm called batch gradient ascent to climb up a mathematically concave hill. By taking these calculated, careful little steps upward, we eventually find the absolute best parameters that maximize the probability of our classifications. And that leads us to our final section, number 5, the need for speed, featuring Newton's method.
Here's the final roadblock we've got to tackle. Gradient ascent is kind of like a tiny ant taking these blind, cautious baby steps up that mountain of probability. Sure, it works, but man, it can be painfully slow for our algorithm to actually process. Sometimes it requires many thousands of iterations just to reach the peak. So, to save the day, we bring in Newton's method. Imagine replacing that slow-walking ant with a literal mathematical catapult that shoots you straight toward the peak. Newton's method brilliantly uses tangent lines, basically straight-line approximations of the curve's angle, to calculate exactly where that tangent hits 0. Instead of taking those tiny baby steps, it calculates massive, highly accurate leaps directly toward our final answer.
This grants us what is literally a mathematical superpower, called quadratic convergence. With quadratic convergence, the precision of our model doesn't just incrementally increase, it effectively doubles with every single leap it takes. Think about the power of that for a second. If your error is 0.01 on one step, it instantly drops to 0.0001 on the very next step. Bam! It requires drastically fewer iterations than gradient descent to find those absolutely perfect parameters.
But of course, there's a trade-off. There always is, right?
While gradient ascent takes slow, cheap baby steps, its cost per iteration is incredibly low, which actually makes it absolutely perfect for giant models with millions of parameters. Newton's method, on the other hand, takes those giant, rapid leaps, but the underlying math requires something incredibly taxing, inverting this massive, complex grid of calculations called a Hessian matrix. If you've got 10,000 parameters, you have to invert a 10,000 by 10,000 matrix on every single step. That is computationally exhausting and incredibly expensive. So we're left with a clear choice: deploy the slow but steady gradient ascent for massive models, or fire up the lightning-fast but expensive Newton's method when our parameter count is a bit smaller.
Wow, okay, we have covered some incredible ground in this explainer today. We've evolved our understanding from simple parametric straight lines all the way to non-parametric curves. We've uncovered exactly why least squares maximizes probability, tackled high-stakes binary classifications using that elegant sigmoid function, and dramatically sped up our algorithms using the sheer power of Newton's method. So, now that you know the math under the hood isn't magic, but rather elegant probability and giant calculus leaps, are we closer to building true artificial intelligence, or are we just doing some incredibly fast curve fitting? What do you think?